Welcome to this conjecture lecture about the long outstanding binary Goldbach conjecture, first propounded 280 years ago, but not yet proven until now. In 1742, Christian Goldbach wrote to Leonhard Euler suggesting what's now known as the ternary conjecture, that any odd integer greater than or equal to 7 is in at least one way the sum of 3 primes. Euler replied, stating the binary conjecture, that any even integer greater than or equal to 4 is the sum of 2 primes in at least one way, but he said he couldn't prove it. Karl Popper in 1963 wrote of the binary conjecture, "We don't know, perhaps we may never know, and perhaps we can never know whether it's true." Schnirelmann in 1930 showed that any integer 2m is the sum of not more than 20 primes. Vinogradov in 1937 and Chen Jingrun in 1973 showed that any large enough 2m is the sum respectively of not more than 3 primes and of a prime and a composite with not more than 2 prime factors. But the conjecture itself has remained open until now. We begin with the frame of reference, the box of constraints within which we shall deploy what I hope you will agree is a formal proof of the binary Goldbach conjecture. First, the method that we're going to use. For all the integers m between 2 and 13, Goldbach partitions are already known. What we're going to show is that for m at least equal to 14 and all the way up to infinity, the count t sub 1 of true Goldbach partitions, that pairs of integers both of which are primes and which sum to 2m, will be no less than an estimated minimum quantity e sub 1 that will itself necessarily be positive. In other words, that t sub 1 is greater than or equal to e sub 1 greater than 0, and therefore that t sub 1, the true number of Goldbach partitions, will always be positive. That's the method. Now we define some key variables. The target integer m will be at least equal to 14, and all the odd integers s will fall in what we'll call the window of opportunity between 3 and 2m minus 3. And we dispose all those odd integers in q equals the ceiling function on m minus 2, all divided by 2, distinct partitions S1, S2, those are the two elements in each partition, and in each such partition S1 plus S2 must sum to 2m. Then we take px as the greatest odd prime whose square, px squared, does not exceed 2m minus 3. And we recap that T1 is the true quantity of Goldbach partitions in that window of opportunity in relation to any m, and E1 is the estimated minimum quantity that we would expect to see in that window of opportunity. And we'll take an example. Suppose m was equal to 34, then 2m is 68. The window of opportunity is then between 3 and 65. So we arrange all the odd integers s1 and s2 between 3 and 65 as shown in the bar across the middle of the screen. And the partition count q is simply the ceiling function on 32 over 2, which is 16. But it's worth noting that for every partition count q, the number of partitions that fit in the window of opportunity, there are two potential values of m. m is 34 here, but it could also be 33. You could start the S2 row with 63 rather than 65, shifting all the row to the left and then putting another 33 at the right-hand end of that lower line. And that would also be a valid distribution of the integers, in this case between 3 and 63. And this is where the ceiling function comes in, because it's also 16 for m equals 33. In other words, the ceiling function on 31 over 2, which is the ceiling function on 15.5, rounds up 15.5 and makes it 16. Now the Goldbach partitions S1, S2, such that S1 and S2 are both prime, are shown here in green. Now we need a lemma, an intermediate result, which we prove as we go and rely upon later. Where px is the greatest odd prime whose square, px squared, doesn't exceed 2m minus 3, any odd integer s less than px plus 1 squared that stands between 3 and 2m minus 3 in such a way that no prime pn between 3 and px is a factor in S, is itself prime. And if S were the product of more than two factors, or two or more factors, PA and PB, let's say, each greater than PX, then S would exceed PX plus 1 squared, and that's contrary to the definition of S. That's why that lemma is true. If any prime Pn all the way up to Px divides S, then S is not prime. But if none of the primes between 3 and Px are a factor in S, then S will necessarily be prime. So then we set out the minimum and maximum values of M and Q, that's the target integer and the partition count that corresponds to that target integer, for any value of Px. And these equations are easier to derive, so I shan't derive them here. I shall simply state that they are so. And there's a table there so that you can see how they work. And you can see that they will, between them, cover all of the values of m all the way up to infinity if you extend the table indefinitely. So nothing much more needs to be said about that, but it is actually helpful to be able to express, for instance, q min as being equal to px squared minus 1 over 4. It's helpful to know that, as we'll see later. Now we're going to apply what we've learnt during the reference frame stage to the integers using the sieve of Eratosthenes, a classical technique. Eratosthenes of Syene, from 275 to 194 BCE, was the polymath librarian of Alexandria. He devised the eponymous sieve by which all multiples of successive primes up to px are eliminated from a sequence of integers that is less than px squared, after which all surviving integers, by lemma 1, in that sequence must be primes. Now the sieve of Eratosthenes is applied x times. Each odd prime Pn from Px to 3 in descending order eliminates all partitions in which Pn is a factor in either S1 or S2 or both. After the nth such sifting, the estimated minimum survivors, E sub n, will be equal to E sub n minus 1 times Pn minus 2 over Pn, taken as a floor function. And a floor function is simply the integer part of the number. So the floor function on 7.85, for instance, would simply be 7. You knock off everything after the decimal point. And after the final sifting, the true quantity T1 of surviving partitions will not be less than the estimated minimum E1. And by lemma 1, any such survivors will be true Goldbach partitions. Let's take an actual real-world example. Let's let m equal 34, as we saw before, and px then equals 7, and the prime divisors are then 7, 5, and 3, which we apply successively, using each of them to sift the partitions. Now the odd integers s from 3 to 65, that's our window of opportunity here, are disposed in Q equals 16 partitions, S1, S2, from 365 to 3335. 365 is on the left there of the yellow bar, and 3335 on the right. In each partition, S1 plus S2 is equal to 2m. And after all siftings, we will show that T1 is greater than or equal to E1. So let's now do all the siftings, and we'll display them all on the screen at the same time in 3 panels. The one at the top is for n equals 3, and that's Pn equals Px equals P3 equals 7. And there are 4 partitions in which 7 divides one or other of the elements in that partition. So they get knocked out. They can't be go-back partitions, leaving 12 of the 16 to fight another day. We go on to the middle panel where P2 equals 5. We knock out another 5 partitions, leaving just 7 remaining, and then we go down to P equals 3 in the bottom panel. Another 5 get knocked out, leaving just 2 remaining. So has lemma 1 worked? Well, yes it has, because the 2 remaining are 7 and 61 on the left there, marked in yellow, and 31 and 37 on the right. And all of those are indeed prime numbers. So we have 2 go-back partitions. So our true number is 2, and as we see, by the simple method of calculation that we use to estimate how many survivors there will be, there are also 2 expected survivors, and sure enough, that's what we find. Now I'm going to start the proof in earnest with what I'll call the key relation. Now this looks terrifying at first sight, but it's actually rather simple. We start with the true quantity of surviving partitions after all sifting stages, and that will be, they'll all be go-back partitions by lemma 1. And we see that that is the product of Q and a succession of fractions, proper fractions, Pn minus 2 over Pn for diminishing values of n, starting with n equals x and going down to n equals 1. And you can see that if you apply this, it's quite complicated because these are all prime denominated proper fractions that are all multiplied together. And so it's quite hard actually to calculate the true number of partitions from this. So all we do is we say that's approximately what it's going to be. And the beauty of this particular method of proof is we don't need to know exactly what it's going to be. All we need to know is that it's going to be at least equal to a number that we can calculate, and that is E1, which is the second line down in the blue bar across the center of the slide. And there you can see it looks quite similar, but there are some additional factors in there which I'll talk about later. All we'll say at the moment is that T1 is necessarily greater than or equal to E1 as a result of the presence of those factors. But then these nested floor functions, it would be nice if we could telescope them and make them into an easily tractable quantity. But it appears that we can't, because we're having to do all these nested floor functions. Well, I'm going to assert, and I shall of course later prove, that you can knock out all the floor function symbols except the one on the outside. So you have a single open floor function, which is the third line of this key relation, and then you can telescope that down to simply Q over Px taken as a floor function, which begins the fourth line of this relation. Now we know that Q over Px must be greater than or equal to Q min over Px, and we saw what Q min was as part of the reference frame, and we know that Q min over Px, again part of the reference frame, is equal to Px squared minus 1 over 4Px. And if you divide the top and bottom by Px, then you know that that is greater than or equal to Px minus 1 over 4, taken as a floor function. And that in turn, where Px is greater than or equal to 5, must of course be greater than 0. So E sub 1, which is our estimated minimum number of go-back partitions, will necessarily be greater than 0, and T sub 1 will necessarily be greater than or equal to E sub 1, and is therefore positive, and therefore there are always go-back partitions. So that's how the proof is going to work. And let's now prove each stage of that key relation. First we take the comparison between the true and estimated minimum survivors. What's the difference between these first two lines of the key relation? And we can see that in the second line for E1, there are some additional composite denominated proper fractions which exist in E1, but they're not in T1. And because they're proper fractions and they're part of a product, those proper fractions, being less than 1, will reduce the value of E1 compared with T1. And that's why E1 cannot be more than T1. So for any Px greater than or equal to 11, these composite denominated proper fractions begin to come into play. And so the estimated minimum E1 having these particular additional proper fractions in it, which are absent from T1, diminish E1 compared with T1. Now the prime number theorem shows that the fraction of composites among the integers less than or equal to 2m is approximately 1 minus 1 divided by the natural logarithm of 2m, and that will of course increase with 2m as the fraction 1 divided by the natural logarithm of 2m of primes among the integers declines. Thus, not only is it true that T1 will be greater than or equal to E1, but also that the difference between T1 and E1 will increase as Q and M and Px increase. And we can show this in this diagram here by Richard Tobin of Edinburgh, to which I've added a dotted line at the bottom, which is the estimated quantity of Goldbach partitions surviving after all sifting stages, and T1 is expressed by the Goldbach comet, which is very colourfully disposed by Mr. Tobin up above, and you can see that the gap between our dotted line for E1 and the true number of Goldbach partitions, which is shown by that comet, for all values of 2m from 4 to 1 million, that gap widens as 2m increases. So now we go on to the telescoping nested floor functions. And here we are saying that in lines 2 and 3 of the key relation, there are two expressions for E1, one of which is a series of nested floor functions, and the other of which, the second of which, is simply a single floor function on the product of Q and all those successive proper fractions, here both prime denominated and composite denominated in strict sequence. And I'm going to assert, indeed I have asserted, that these two, though they may not look equal, actually are. And here's the proof. We take the special case where Px, the largest prime divisor in the window of opportunity, divides Q. In other words, it's a factor in Q, and that means that Q divided by Px is a whole number. It's an integer r, and that in turn implies that Q is equal to r times Px. Then the high value of E, which is of course where we're using Px as our filter, is going to be equal to Q times Px minus 2 over Px, which is equal to r times Px over Px minus 2 over Px, which is equal to simply r times Px minus 2. Now the values of En after n successive siftings will be the integers r Px minus 2 that we've just seen, r Px minus 4, all the way down to 5r, 3r and r, so that after the final sifting, E1 will simply be equal to Q over Px. No need for floor functions at this point because we're using integers all the way through the sifting. And therefore E1 simply equals R. And likewise, if we took Q as being equal to R plus 1 plus P, then E1 would be equal to R plus 1 after all sifting stages. So now we're ready to look at the general case where R times Px is less than or equal to Q, which in turn is less than R plus 1 times Px. Well, then it follows that R plus 1 will be greater than E1, and E1 of course can't be greater than R, and therefore E1 taken as the floor function Q over Px must be R. It can't be anything else. It can't be less than R, and it can't be R plus 1, and it can't be a fraction because it's a floor function, so it must be equal to R. And therefore the nested and open floor functions for E1 are indeed equal. And we can see that on this slide with a worked example where px equals 11 and q is on a window of opportunity here from 33 to 43, and r is therefore equal to 3. And if we take the column in green for 33 towards the left of the table, you can see that the successive values of e, starting off with 33, go down to 27, 21, 15, 9 and 3. And all of those are multiples of r equals 3. But then, if we go between q equals 33 and q equals 44, but not quite as far as 44, then we see that sure enough, after all these filtering stages, E1 is indeed always equal to 3. It cannot be anything else. And we also know that the floor function on q divided by 11 must also be exactly 3, and for the same reason, and so they are equal. Therefore, we can say that E1 is always equal to the floor function on E2 over 3, and that's a way of representing the fact that we've gone through all the sifting stages one by one down to E2 and then finally E1. That is equal to the telescoped value q over px taken as a floor function. That's here q over 11, which is equal to r, which is equal to 3. But let's take a worked example numerically. Let's take, just arbitrarily, the 10,000th odd prime. So p 10,000, x then is 10,000. Px, the 10,000th odd prime, is 104,743. Then the minimum value of q, as you'll see, is 2.7 billion plus. And E1 is q min divided by px, which here comes out to 26,185. But if we'd done that in stages, after the penultimate sifting by nested floor functions, then E2 is equal to 78,556. After the final sifting, this is the 10,000th sifting, E1 is simply equal to E2, the previous estimate, divided by 3, and bingo, it's 26,185. So that was my way of just checking that this really does work, and we have indeed proved it. And it's worth noting that in this example, T1 is equal to 18 million plus, which is greater than 720 times what E1 is, and yet E1 is healthily into the tens of thousands. So now we can do the final accounting that just wraps up the proof. We can see here that T1 is greater than or equal to E1 because of the composite denominated proper fractions in E1 that are not in T1. We can see that E1 is the telescoping product of nested floor functions, and that comes down to the floor function on Q over Px. That in turn, by the frame of reference calculations and equations, must be greater than or equal to Q min over Px, taken as a floor function. And that in turn, we know, is equal to Px squared minus 1 over 4Px. If we divide the top and bottom of that by Px over Px, we say that that is greater than or equal than to Px minus 1 over 4. And it is evident just looking at that if Px is greater than or equal to 5, then E1 will be greater than 0, therefore so will T1, therefore there are always Goldbach partitions for all m where Px is greater than or equal to 5. And we already know that that's the case for all m where Px equals 3 or 2, and therefore for all m greater than or equal to 2, Goldbach partitions necessarily exist. That's the proof of the binary conjecture. Job done. But wait, there's more. We can apply exactly the same method to the twin prime conjecture. In 1846, de Polignac conjectured an infinitude of consecutive primes differing by any gap 2g greater than or equal to 2. And the lower end of that conjecture is, of course, a gap of just 2 between a pair of primes. And that's the twin prime conjecture. It's a special case of the general de Polignac conjecture. Now, Brun in 1919 showed that the sum of the twin primes reciprocals converges to his constant. The famous Hardy and Wright, great number theorists, wrote that proof of the twin prime conjecture is at present beyond the resources of mathematics. Well, as I shall submit, not anymore. Brent in 1976 and Nicely in 2010 derived Brun's constant from twin primes less than 10 to the power of 11 and less than 2 times 10 to the power of 16, and you'll see the two respective values for Brun's constant that they obtained thereby at the bottom of the slide. Well, Goldstone, Pintz and Yildirim in 2009 showed that an infinitude of consecutive primes differ by 16, but under the assumption of the as yet unproven Elliott-Halberstam conjecture. Yitang Zhang came along in 2013 and showed that without assumptions, infinitely many consecutive primes differ by 70 million. Now this astonished the world. Nobody had done this before. They'd not found any prime gap which we knew would go on to infinity. But here it is. Yitang Zhang did that. And then a collaboration moderated by Terence Tao in 2014 reduced their prime gap rather spectacularly from 70 million to 246. But still a long way from the 2 that we're looking for. So once again, the frame of reference. And the first element in the frame of reference is the pivot between twin primes. If the twin primes are px and px plus 2, then their mean, which is simply the number that's between the two, it's an even number, is px plus 1. Now, since the difference between the squares of px plus 2 and px is equal to 4px plus 4, the quantity q of even integers s on that interval between px plus 1 and px plus 2, px squared plus 1 and px plus 2 squared minus 1 will be simply half of 4px plus 4, in other words 2px plus 2. However, since px squared plus 1 and px plus 2 all squared minus 1 cannot be themselves candidate pivots, because if they were, they would be next door to squares, and squares are not primes, then q in fact equals simply 2px, and that's very useful because it means no more of those tiresome floor functions to account for. We also need a lemma, and here for any pn, any prime pn which is less than or equal to px, no even integer s is congruent plus or minus 1 modulo pn will be a true twin prime pivot, because otherwise pn would be a factor either in px squared or in px plus 2 squared, in which event s could not be the mean of 2 primes. Now the analogue of the sieve of Eratosthenes will now be applied. This is similar to the sieve. It works in very much the same way. And for successive primes going from px all the way down to p1 equals 3 in descending order, all candidate pivots s congruent to plus or minus 1 modulo pn are eliminated in successive stages. And at the end of that process, E1 will be equal to q times p1 minus 2 over px, which is equal to q over px, which is equal to 2. So our estimated minimum number of quantity of prime pairs in any window of opportunity will always be 2. There will always be at least 2 there. And by lemmas 1 and 2, each final pivot marks twin primes. So the estimated minimum E1 equals 2 includes, as before, composite denominated proper fractions absent from the true count T1, so that T1 minus E1 will again tend to increase with Px. The key relation shown on the screen is much simpler than for the Goldbach conjecture, no tiresome floor functions, and we can see that yet again T1 is greater than or equal to E1, which is always equal to 2. So T1 must be at least equal to 2. There must always be twin primes all the way, for whatever value of Px you take, all the way up to infinity. And we can take an example where Px equals 11, Q therefore is 2Px, it's 22, and therefore our window of opportunity is 11 squared plus 3 to 13 squared minus 3, because of course 11, 13 is a known twin prime. So we do the sifting of each of the 22 candidate pivots modulo px equals 11 down to p1 equals 3, 11, 7, 5 and 3 in successive sifting stages, knocking out all of those pivots that are congruent to plus or minus 1 modulo pn. And so we end up with exactly 2 true pivots surviving, and that happens in this instance to be equal to the minimum estimated, which is also 2. And in fact, if we look at the first 10 pairs of known twin primes, that's from 35 to 107, 109, then the new true pivots occurring between the squares of each of these pairs of twin primes are, in the first 5 instances, always the minimum that we have calculated, which is 2. So this does kind of work. And then, exactly as we'd expect, because of the influence of the composite denominated prime factors in E1 that are not in T1, T1 will gradually grow in respect to E1. And sure enough, in the second half of this table, we see T1 becoming bigger than 2. Now then we can also look at the first pair, 3, 5, of twin primes, and this on its own generates an infinite series of further twin primes, as do all the other twin primes. So on the interval from 3 squared plus 3 to 5 squared minus 3, the first window of opportunity, there are 2 new twin primes. If we square them and then take the interval between those squares, there are 6 new twin primes. If we square those and take the interval between them, there are 250 new twin primes, the first of which is more than 357 million. And you can carry on with that ad infinitum. We've proven that. And the final accounting is very straightforward. It's quite similar to that for the Goldbach conjecture. T1 is greater than or equal to E1 because the composite denominated proper fractions in E1 are not in T1. The telescoping product is then taken, it's q over px, which is equal to 2px over px by the reference frame, and that is always equal to 2. And since the true number T1 of new twin primes between the squares of twin primes cannot be fewer than E1 equals 2, there exists an infinitude of twin primes. Job done. Twin prime conjecture proven, or so I say. And there's a rather nice visual verification that we can make of this, and I was very pleased when I stumbled across this because it does appear to indicate that we're on the right track here. If we go back to that wonderful diagram of the Goldbach comet by Richard Tobin of Edinburgh, and we then compare it with a twin prime comet, and this time there's another coloured one, and this is done by Strasimir Popvasilev, originally of Bulgaria, we see that these two patterns, these two comets, are strikingly similar. Well, now, of course, I submit, we know why. It's because you can prove that they are going to be similar because we've proven both of these by much the same method. But wait, there's more. Why stop at the twin prime conjecture? We can go up and look at the cousin-prime conjecture. And we've also proven that. Now, as we saw, the twin prime conjecture is the lower bound case, the gap 2g equals 2, of the de Polignac conjecture of 1846. The gap is just 2 between the twin primes. For 2g equals 4, the gap between the twin primes is 4, and these are known as cousin primes. And for any px, the candidate pivots are the odd integers on our new window of opportunity, which is px squared plus 4 to px plus 4 all squared minus 4. There are thus 4px plus 5 candidate pivots S, so that there are the floor function on 4px plus 5 divided by px, which is simply equal to 4, estimated minimum survivors E1 after all siftings and for all windows of opportunity. And that one further difference between this and the twin prime proof is that no true cousin prime pivot S may be congruent to plus or minus 2 modulo Pn for any Pn from 3 all the way up to Px. Now we take an example of the sifting process, again, the sieve Eratosthenes or its analogue, and here we take px equals 7, q is then 4px plus 5 or 33. The candidate pivots then on the window of opportunity are 7 squared plus 4 to 11 squared minus 4. There are 33 of them. You see them there, and we then sift them out, modulo 7, then 5, then 3, and all candidate pivots congruent to plus or minus 2 modulo Pn are eliminated. And sure enough, where we would predict that there would be at least 4 survivors, that's E1 after all these sifting stages, there turn out actually in this instance to be 5. So once again it has worked. And once again, as with the twin primes, so the first pair of cousin primes, 7 and 11, on its own generates an infinite series of further cousin primes, each new set of cousin primes occurring between the squares of the previous pair of cousin primes. And so, for instance, on 4,513 squared plus 4 to 4,517 squared minus 4, that's a fairly big window of opportunity. There are 175 cousin primes, the first of which has a term px which is greater than 20 million. And of course you can go on doing this ad infinitum, as we have proven, and the final accounting just confirms that. It's very similar to the final accounting for the twin primes, but with one important difference. Here, the pivot between cousin primes always has a factor 3, and that means it's composite, just as the pivot between the twin primes had a factor 2. It was even, and therefore was composite. So we do have to show that there are no primes between the pairs of primes, in this case separated by 4, the cousin primes. And it's very easy to show that, and therefore there does exist an infinitude of cousin primes. Job done, cousin-prime conjecture proven, or so I submit. But wait, is there more? Sadly, no, there isn't. There is, of course, the general de Polignac conjecture. I strongly suspect that with the work we've done here, it should be possible to crack that one too, but I haven't done it yet. I haven't tried, actually. But what we can say is that there is a difficulty with the general case that doesn't exist in those first two instances where 2g is equal to 2 and 4, respectively. Though the present method shows mutatis mutandis that infinitely many pairs of primes are separated by any given gap 2g, where 2g is greater than 4, the primes px and px plus 2g in each pair may not necessarily be consecutive. So I haven't spoiled all your fun. There's still some work for you to do. So I end then with some acknowledgements to those who have held my hand on the way to this, I hope, not uninteresting result. And I'm dedicating this work to the memory of the late Professor Freeman Dyson, who I think was the world's greatest living physicist of his day. And he was kind enough to give me some time at the Institute for Advanced Study in Princeton. Some years ago, we strolled in the grove behind the Institute, and we talked of this and many other things, for his was a mind that had a wide range of interests. Of course, he was an Englishman, and as George Santayana said, England is the paradise of eccentricities, hobbies and humours. Well, he, like me, had many hobbies, and so he was intrigued by the notion that it might be possible, I hadn't then done it, to crack the Goldbach conjecture. And we did discuss some of the ideas that eventually found their way into the proof I've presented here. So I miss him greatly, and I'm happy to dedicate this result to him. And I also want to thank Professor Richard Taylor of Stanford University, who didn't know me at all. I simply sent him an outline of this work out of the blue. He very courteously, very kindly and very promptly responded with some helpful suggestions, including in particular the fact that I must prove that the nested floor functions are equal to the single floor function that gives you the value of E1. So to him too then, I am most grateful. And I have provided references to all of the works that I have cited during this lecture. And while those references appear on the screen, I should like to offer to anyone who has been gallant enough and brave enough and persistent enough to travel with me this far, that if you would like a copy of the 5-page paper in which these 3 long outstanding conjectures are in my submission proven, then do write in. My email address is on the header slide, and I'll send them to you. And also you may like a copy of these slides to play with, in which case just ask for that and I'll send that to you as well. And with that, thank you all for coming with me on this little journey into the arcana of number theory. And good day to you all.